13.3, we're going to look at the fourth and the last of our conic sections, namely the hyperbola. So here's a schematic on how a hyperbola could be created. We have a case where this is a double nap cone, and if a flat surface crosses both naps of the double nap cone at an angle such that we create these two impressions outside of the two cones, each nap of a cone, the upper and the lower nap of the cone, then the resulting sections are referred to as a hyperbola. So this would be the three-dimensional version of a hyperbola with impressions on the double nap cone, and this would be, of course, the projection of those branches onto the plane. Now, as far as the terminology goes here, each of these pinkish kind of salmon color branches are just that. They're called branches of the hyperbola. The center of the hyperbola is right in here, and the low point here and the high point here, these are called the vertices. Each of them is a singular vertex. So together there are two vertices for every hyperbola. And here's a case where the axis of symmetry of the hyperbola runs through the center and goes right through the vertices. Now, because this axis of symmetry is vertical, we often refer to these types of hyperbolas as vertical hyperbolas. And just as with parabola, circle, and ellipse, we are interested in the equation of these hyperbolas. So here we go. First, we're going to look at the hyperbolas that are centered at 0, 0. And here's the equation of those hyperbolas. The hyperbola could start with x squared over a squared minus y squared over b squared equals 1, or you swap out the position of x and y and you get another equation of a hyperbola. We saw a similar equation with the ellipse. Indeed, if the subtraction here, the minus sign, you change it to a plus sign, the resulting conic section is going to become an ellipse, which we covered in the previous section. And remember, I mentioned the key to our success in chapter 13. And by success, I mean successfully being able to graph these conic sections, is to recognize the form of the conic section. So here, if there is the subtraction between the two squared terms, then we know that this is going to be a hyperbola. Now, if the equation of the hyperbola starts with x, then the axis of symmetry is going to be a horizontal axis. And if the equation of the hyperbola starts with y, then the axis of symmetry is going to be a vertical axis of symmetry. Now, just like we have here, we have the equation starts with y, and therefore the vertical axis of symmetry is going to be just that, vertical. Now, the axis of symmetry, by the way, it's also called the transverse axis. Remember, the word transverse here means a side-to-side line that is drawn relative to some forward direction. So, again, the axis of symmetry of the hyperbola is also known as the transverse axis. And here, by the way, this is a page from the book. This is where your exercises are. Again, I highlight the ones that are part of your homework problems. And I will do quite a few exercises in this section for you, and you will see how these turn out. But there you go. Here's the balance of the homework problems. And also, you're going to see later on the next page, I believe there's more homework problems on the next page, but I'll show you that in a minute. So let's begin by going over exercise number 10. Okay, that's this one. You're looking at number 9. We're going to look at number 10. Now, in number 10, because the equation starts with y, so we know that this is going to be a vertical hyperbola, meaning the axis of symmetry is going to be vertical. So here's how we're going to start this. Again, because we recognize the form of this, the center is going to be at 0, 0, and this is what we mean by vertical hyperbola. It means the branches open up and down. If you start with x squared, the branches open to the sides. Okay, now what we need to do is actually, we're not going to plot points. Again, we're not going to plot points, but this is how actually the hyperbola is graphed, and I'll explain what I've done in here. Okay, so because the center is at 0, 0, so we're going to start from the center. This is 0, 0. Remember, I'm at the center. Now we know that we're looking for a vertical hyperbola, right? Now because of that, at this point, we're going to look at the square root of 16. I'm looking at the denominator of y squared. You see that 16? We're going to take the square root of that. It's going to be plus minus 4. And because of the y, that means in a vertical direction. So from the center, I'm going to go up 4 and down 4. And that's what I indeed have done from the center, from 0. You go up to 4, and this is where I'm again. I'm at center. Here's 0, 0. So I went up 4. From the center, you go down 4. And then you look at 9. Here, square root of 9 is going to be plus or minus 3. And the x tells me I need to go in a horizontal direction from the center. So square root of 9 plus minus 3. From the center, you go to the right 3, and then you go to the left 3. Now, at this point, we draw what we call a fundamental rectangle. That's what this is. So I'm actually drawing this fundamental rectangle, and the way you draw it is you just go through those the outline of those points that we had. Remember, 3, negative 3, 4, negative 4. Just draw a rectangle through those 4 points. And once you have drawn the rectangle, next we're going to draw the diagonals. Okay, and there you go. This is one diagonal, and the other one is this one right in here. This is a diagonal. Okay, so let me point to them. Here's one diagonal, and this is another diagonal. If you draw a line corner to corner, you create the diagonals. Now, these lines that I've drawn that go through the corners of this fundamental rectangle, they're called the asymptotes. Each of them is an asymptote. So these are the two asymptotes. They are not part of the graph, by the way. Everything that's in dotted format is not part of the graph. It's like scaffolding on a building. It's something we're going to build the branches upon. Okay. Now, once we have the fundamental rectangle and we have these asymptotes drawn out, then because we know we're looking for a vertical hyperbola, so at this point, from the center, I go out to the edge of the box. So you go up 4, out to the edge of the box, the lower point, negative 4. And then you draw the vertices. I mean, not draw it, but you locate them, you point them out. And then you draw the branches just like I have here. And make sure these branches do not cross the asymptotes, the diagonals. And that's what they're asymptotes. In this case, the graph of the hyperbola will not cross nor touch the asymptotes, but it will simply approach it. Same thing with this lower branch. The lower branch I've graphed it this way and this way. Note again, I did not plot any points. I didn't assign a value for x and see what y turns out to be. So the specifics of this hyperbola, the vertex, one of them 0, 4, that's this one. The other one, I call it VV prime. V prime is 0, negative 4. And those are the key points on the graph. Now, the distance from 4 to negative 4 and negative 3 to 3. So here I have, this is what I have in green. So the line segment that connects the vertices, this is called transverse axis. And the other line right in here that helps us create this fundamental rectangle, this is called the conjugate axis. So every hyperbola has a transverse axis and a conjugate axis. Remember, transverse axis connects the vertices of the hyperbola together. So just want to mention that as well. Now, let's take a look at another exercise here, number 12. In number 12, again, we want to graph this hyperbola. Now notice this time the hyperbola starts with x squared, so we know that this is going to be a horizontal hyperbola. So what do we mean by horizontal? That means the axis of symmetry, which is the transverse axis, is going to be horizontal. That's what that means. So all we are lacking are the specifics that allows us to actually graph them. So the center is at 0, 0, and here I have graphed this one. Notice again, I did not plot any points. So what did I do first? First, I located the center. So this is the center. Okay, I located the center of the hyperbola. Then I look at the denominator of x squared. Okay, right in here. The denominator of x squared is 25. So take the square root of that. We're going to get plus or minus 5. So at that point, from 0, I went to the right 5. And then from 0, I went left negative 5. And those become the vertices, right? Because we know this is again a sideways hyperbola. Looking at the denominator of y squared, 36. Take the square root of 36, we get plus or minus 6. So from the center, I'm going to go up 6. And from the center, I'm going to go down 6. And then I graph this green box, which is the fundamental rectangle. I graph this one through these 4 points. And then drew the corner to corner, the diagonals in each box. And once I have done that, then I can pretty much draw the branches. So again, from the center, you go to the edge of the box. And from the vertex here, I just drew this branch. And then I drew the left branch of that hyperbola. And again, I just make sure that the branches approach these diagonals. The graph in blue is the graph of the hyperbola. Everything else is just extra. Okay? And that's how you graph this one. Now, next, we're going to look at hyperbolas that are off this origin. Remember, everything we've looked at so far has center at 0, 0. So what if the center is not at 0, 0? So we're back to our HK form of the hyperbolas. So here is the HK form. X minus h squared over a squared minus y minus k squared over b squared equal 1. Two things here. Definitely need to have the 1 here. It's very important to have this 1 on this side. And also between the two fractions, there is a subtraction, right? A minus sign. So if you turn that into a plus sign, then the result's going to be an ellipse. So again, recognizing the form of the conic section is the key in being able to graph these correctly without plotting a single point. So for this one, because the fraction starts with x, these are the ones with horizontal transverse axis. Okay, so for this one, if I was to draw this one, actually beginning with x, yeah, this is going to be horizontal. So the transverse axis, let me erase this one. It's not vertical. It's going to be a horizontal because we start with x. So we have horizontal transverse axis, and this is what that means. Okay, and remember, the vertices of the hyperbola should be on the transverse axis, and they are here. If the hyperbola begins with y, so this one is the one that has actually a vertical transverse axis. So I'm glad I caught that one. And there you go. It's going to be a vertical transverse axis because the hyperbola's equation begins with a y here. Okay, y squared. So that's how we know it's vertical. If it starts with x squared, then it's going to be horizontal transverse axis. Okay, now we'll look at an example here. So this is, I didn't assign any homework problems here, but it's good to know. I'm going to do one of them, as long as you can do like something. If you want to try number 57 here. There you go. Try that one and see how it turns out. Both of these are going to be horizontal, right? If you want to do, by the way, any one of these other ones, 59 through 62, what you need to do in the case of, for example, number 59, because we need to have 1 on this side, see that is 32, so divide by 32 everything, this one, and this one, and then you get something that looks like 57. Same thing with this number 60, divide by 100, divide by 100, divide by 100 this time, and you get something that's similar to this one. Now you got to be careful in number 59 because we start with y. So number 59, these are going to be vertical hyperbolas. Number 60 is going to be horizontal because it starts with x. And these other ones, don't worry about. You can work these by completing the square method if you choose to, if you just want to practice with those. But let me do one just like number 58 here. So we're looking at this one actually, number 58. Now, for number 58, in the center of this, hyperbola, the center is going to be at h, which is 2, and k is 1, right? Remember hk, this is h, 2 is h, and k is 1. Let me just put that. Here's h, and there is k. So the center is at 2, 1. So we're going to go to 2, 1, and here's the center right there. That's 2, 1. And this is 2, and here's 1. Okay, so there's the center. Now, we're going to, and remember, because we started with x, it's going to be horizontal. That means branches open to the sides. Square root of 9, the denominator of the fraction here, the square root of 9 is 3. Square root of 4 is plus minus 2. So square root of 9, 3, we go right 3, left 3. Square root of 4 is plus minus 2. We're going to go up 2, down 2. So from the center again here, okay, from the center, you go to the right 3, and then you go to the left 3. So that's how you get these vertices. And then square root of 4 was 2. So from the center, you go up 2, and then you go down 2. Okay. And then here I have 1, 2, 3, and 4 points. And the next step is to actually draw this fundamental rectangle. This rectangle, you draw it through these 4 points. And again, we know what we're looking for. We're looking for a horizontal hyperbola. So at this point, from the center, you go out to the edge of the box on the left and to the edge of the box to the right. And then those are the vertices, and you just draw these what seem to be parabolic, right? These look like parabolas. So you draw these parabolic branches. And same thing with this one, this branch, the vertex, and you draw these parabolic branches. Oh, and by the way, these are again the asymptotes, right? I drew this one. The asymptotes, remember, you draw these lines from corner to corner, and that's how you get these lines. The final graph actually is the branches, the parabolic branches is the final graph. Everything else is going to help us. Now, how wide, how narrow the branches get depends on the asymptotes, right? So, for example, if my asymptotes look like this, and I have a horizontal hyperbola, that's going to be like that. If my asymptotes look like that, and my horizontal, there you go, hyperbola is going to look like that. So again, how narrow or wide, how flat these branches get depends on the position of asymptotes. Okay, and we're done with that part. Now, and then we have this other kind of hyperbolas in this section, which are referred to as non-standard hyperbolas. Okay, so these are the non-standard hyperbolas. And they actually have a single term. If you look at here, it's just xy equals c. C is a constant here, right? So you only have one term, x times y. There's no squared, there's no x term by itself, no y term. It's just x times y. Now, I'm going to go through this example in the book together. Now, the fact that x times y is equal to a constant, and in the book's example that we're looking at, example 3 here, the constant is -8. Now we know that x times y equals -8. So that means x and y cannot be 0. Neither can be 0, because otherwise the product would have been 0. And that's what they say here also. So the next step, the fact that x and y are not 0, it allows us to divide both sides by the variable. Otherwise, if we didn't know that, we couldn't do it, because I could be dividing by 0. But here we know we're not dividing by 0 because of what I just said. Now, dividing both sides of this equation to solve for y by x, from this -8 divided by x, you get this one. And they put -8, that was in front of 8, in front of the fraction line. Now, they actually plot points. See, this is something that we don't want to do. But they do, and understandably so, because they want to show you by plotting points what these branches look like, what the whole graph in fact looks like. So they pick some reference points here, 2, -2, 4, -4, 1, -1, 8, -8, and so on. And these are the corresponding y values. So just to give you one point, when x is 2, you plug it into here. 8 divided by 2 is 4. Negative in front makes it -4. When x is -1, for example, when x is -1, you have 8 by -1 is -8. Negative of that makes +8. And there you go. And then they plotted these points. You see that? They got 4 points on this branch. 1, 2, 3, 4 points. Total of 8 points here. And then they connected the dots and they gave that smooth curve which forms each branch of the hyperbola. And of course you have your vertical and horizontal asymptotes. Notice these are also hyperbolas, by the way, interestingly enough, and that's why it's in this section. So in general, we're going to generalize now what we just saw here to graph of xy, and right in here the graph of xy equal to a constant. We'll generalize this in a moment. Now let's see. And in general, in the equation xy equals c, if c is positive, remember in this example we just saw c was -8. But if it was positive, this is what the graph's going to look like. And I want you to just know the general shape of the graph, okay? Don't worry about specific points. We don't want to plot points. Just know the general structure of the branches, how they form. So if the product of xy is positive, then one branch goes in this direction and the other branch is here. One located in Q1, the other one is located in Q3. Remember, these are parabolic branches. And what if the product is, before we look at negative products, here I have actually, I went to Desmos and actually graphed this one in Desmos. So you're looking at 3 equations. This one, xy equals 1, and then xy equals 2, xy equals 3. I have red, blue, and green. So xy equals 1, that's the one. This is the one branch that's in red, and here's the other branch of it. Xy equals 2, that's the one in blue. Xy equals 3, that's the one in green. So you see that all 3 graphs have same general shape. It's just depending on the number that they equal to. If this is positive, the effect is how it bends right around here, right? See how it curves? So that's what this number 1, 2, 3 will affect. And again, if you look at what I have up here, if the product is positive, this is the general shape, and this just reinforces that. Now, what if xy is equal to a negative number? The product is negative, just like the book's example. Well, all of those are going to look like this. Okay, if it's negative. So one branch will be in the second quadrant, another branch will be in the fourth quadrant. Example of these I have for you again. So the same 3 I had above earlier, I changed 1, 2, 3 to -1, -2, and -3 for you. So the curve in red again, that's xy equals -1. See, one branch in second quadrant, another in the fourth quadrant. When it's blue, you have a branch in the second quadrant and another one in the fourth. The green, you have a branch here and another branch in here. And there you go. Remember, we want to know general shapes. Don't worry about plotting points. Now, so with that, by the way, we're done with all conic sections. To wrap up, we have 4 conic sections in sections 1, 2, and 3. Section 1, we talked about parabola and circle. Section 2, we looked at ellipses. And in this section, we just finished looking at hyperbolas. Now that we've gone through all 4 of them, we're going to actually look at something interesting. This segment has to do with how do we classify a conic section as any one of those 4 graphs that we just talked about. The general form that we're looking at, this is a polynomial form of all conic sections. In fact, parabola, circle, ellipse, and hyperbola, all of those, the ones we just talked about over the last 3 sections, if you expand them, they all follow this general polynomial equation. Okay, now how do we know, or how does this turn out to be a parabola, a circle, ellipse, or a hyperbola? This equation, this long equation. Well, the secret, the key is 2 numbers, a and b. Okay, now a and b, remember, those are the starting numbers. Ax squared, by squared, cxy, that's the product we just saw. dxey equal f. Oh, this xy, by the way, let me go back up here. The parabola, the hyperbola that we saw here, this one. Sorry to take you back up here, but the ones that are in this form, these are hyperbolas, right? These are what we call oblique hyperbolas. Okay, oblique here means rotated. Okay, so they're rotated hyperbolas. That's what they are. Now, let's see. So how are we going to classify these conic sections? We're going to look at actually this long equation again. This is the general form of all conic sections. Now, it's very important to sort out what a and b are here. A is the number that multiplies by x squared. B multiplies by y squared. Okay, so to get a parabola, either a or b, but both cannot be 0. If both of these are 0, then pretty much we don't have a squared term. We just have xy, dx, and ey. Okay, so that's going to be some kind of an oblique hyperbola. Now, for let's say when a is 0 or b is 0, therefore, if one of them is 0, we get a parabola. And of course, depends on whether a is 0 or b is 0. That's what determines whether we have a vertical or horizontal parabola. But we just are interested in the parabola. Don't worry about sideways or vertical. If the 2 numbers a and b are equal, and neither is 0. So for example, we got 5 and 5, 10, 10, -2, -2, -6, -6. As long as they're equal, then the graph is going to be a circle. And for the ellipse, if these 2 numbers a and b are different, but they have the same sign, so either they're both positive or they're both negative. So for example, I have 2 and 9, -3, -11, like that. Then the conic section is going to be an ellipse. And if a and b have opposite signs, so that's like a 2, this is -5. That's a -7, that could be 8. As long as they have opposite signs, a and b, the graph forms a hyperbola. Now, remember, so it all depends on a and b. The a and b determine which of these 4 conic sections we're going to have. Now, if you only have x, y here, right? cxy and f, only those 2. There is no x term, no y term, no y squared, no x squared term. Then the graph, cxy equal f, only c and f are non-zero. Then this is, of course, going to be a hyperbola, right? And there you have it. And of course, in the book, this hyperbola, there's actually, there you go, we have 2 forms of the hyperbola. Okay, Now, let's see. So with that, let's actually look at some exercises. This would be the last work in this section. Then we'll be done. So here's the equation. Number 26, y minus 4 equal to x squared. Remember, we have to have the standard form. Okay? So that means in standard form, by the way, we have to have a 0 here. You see that? This must be a 0 before we can actually judge what a and b are. And you'll see in some of these exercises that's coming up, just looking at before this is 0, we could make the wrong judgment. Oh, and one other thing about this equation, by the way. In sections 10.1, 10.2, and 10.3, all of the ones that were in the HK form, not the oblique hyperbola, but the ones that were in like HK form, if we expand any one of the ones that we did in those sections, none of them are going to have this xy term in them. Okay, so if there was actually an xy term, if there is an xy term where a and b are present, so in other words, if I have a or b and I have c, a or b, but c must be there. If I had that, the effect of this xy term is to cause the conic section to rotate. So what do I mean by that? So for example, in the case of a parabola, the parabola is going to look like that. That's if the xy term is in the parabola. In the case of the ellipse may look like this. Again, that's the effect of xy. And in the case of a hyperbola, the hyperbola, as you just saw, the oblique hyperbola, the hyperbola may look like that. Okay, so that is what the xy effect is. That xy in this equation, and it's going to make our work a lot more challenging and more involved than we want it to be. So usually in these courses we don't bother with the xy term, so we look at the standard ones. And again, not having the xy term here causes the axis of symmetry to be only horizontal and vertical, not rotated. So there you go. So I got this one to equal 0 by moving to x squared term to the other side. Notice that's my a, and there is no b. Remember, there is a y term. B is the coefficient on y squared. There is no y squared in this equation. So b must be 0. And because b in this case, remember, if a is 0 or b is 0, then you have a parabola. That's what that is. In number 32, before we can decide what this is, we need to move everything to the left, have 0 on the right side. And I did. And there you go. Now, and also I rearranged the term. See how the authors had this moved, term x squared moved here? Because we don't want to just say just what you see here, because it starts with 2 and whatever. That doesn't make this a. A is the number that multiplies by x squared. So in this case, first I brought the x squared over, and here is a is 1. And I moved the y squared, the negative y squared, from right to the left. So now b is also 1. There you go. And then just rearrange 8x, and then put the 2y here, move 13 to the right of that, equals 0. And again, I want to emphasize that this is 0 is very important to have. So a and b are equal in this case, aren't they? Therefore, this is going to be a circle because a and b are equal. Let's take a look at number 40. In number 40, we not quite have the standard form. Remember, to the right must be 0. So what I did first is I moved everything from the right, both terms from the right to the left here. And so I got x squared and 3x squared that combined into 4x squared, right? X squared and 3x squared combined to 4x squared. Subtracted y squared from both sides, and subtracted 49, got 0 here, and we got x squared plus 4. Oh, this should be y squared actually, right? 5y squared, this right in here, that should be y squared. So we got 4 squared plus 4y squared minus 49 equals 0. And once everything is simplified, a is 4 and so is b. Remember, a is the number in front of x squared. So because these are the same, therefore this must be a circle. And number 42. Now in number 42, again, because of the 5x squared on this side, first I moved it to the left. I brought 8y to the left also. And after I did, this is what I got. The 5x squared combined with 20 gave me 25x squared. And then I swapped out the terms, the x squared, y squared, to get it in standard form. So a is 25, b is 4. And they are not equal, but they have the same sign, don't they? Means they're both positive. So as long as these two numbers are equal, they're different, and they must have the same sign. So this conic section is going to be an ellipse. And this one, again, we don't have 0 on the right side, so I'm going to move 104x squared to the left, and I did. And of course, we get that all-important 0 on this side, right? Now, a is negative 4, b is 25, correct? They are different, and they are opposite in signs, right? Remember, as long as they're opposite in sign, even if they're equal, doesn't matter. The fact that they have opposite signs, right? A and b have opposite signs. That means this is a hyperbola in number 39. And one last one, I believe this is the last one we're doing. Now look at this one, we got some terms to the right. So I need to, by the way, this is a good example. See, if I just say that's a, that's b, without considering what's on this side, without having 0 on that side, because it would be incorrect what I'm saying, but let's say if I judge that this is a and this is b, they are opposite in sign, so I would say that this is a hyperbola, just like this one, as long as they have opposite signs, hyperbolas, right? But that's judging it too soon. In fact, that is the incorrect answer, because we don't have 0 on the right side. So first, we're going to move everything to the other side, and I did here. So there you go. I moved the 3 terms, right? These 3 terms, I moved them to the left. And then combine like terms. Look at that now. See, they were opposite up here. Now they're the same sign. So same sign, but not equals. That was the definition of a hyperbola, right? No, that was an ellipse. So as long as they have the same sign but they're not equal, then that would be the equation of an ellipse. And there you have it. We don't need to graph these. The idea was just to be able to classify them. Okay, and with that we are done with section 13.3. We only have one more section remaining in this chapter, and in the next section, section 13.4, we will be looking at solving nonlinear systems of equations. But as far as the conic sections go themselves, we are done with the topic of conic sections. So hopefully you followed again everything we did. If not, please watch the video again and see if you can follow what we've done.